All right, good afternoon, everyone. Today, the Atom Seminar has the great pleasure to welcome Professor Matthias Thommes. Professor Thommes has received his doctorate in physical chemistry at the Technical University of Berlin, and he was a postdoctoral research associate at the Institute for Physical Science and Technology at the University of Maryland at College Park, USA. Nowadays, he's a full professor and chair of the Institute for Separation Science and Technology of the Department of Chemical and Bioengineering at the Fredrich-Alexander University. Professor Thommes has authored and co-authored more than 125 scientific papers, reviews and book chapters and patents. And he has been co-chairing various important scientific conferences, such as the CPM workshop series and symposia in the field of adsorption and materials characterization. Once again, welcome, Professor Matthias Thommes. Thank you so much for being here with us today, and please feel free to start your presentation.
Okay, thank you very much for the nice introduction. Thank you very much, Fred, for inviting me for this seminar. I'm very honored that I have a chance to present here my work. And let me, before I start, share my screen. Let me see how we get this done. Okay, and then, so are you seeing now my screen? Is that possible? Hello?
Not yet.
Not yet.
Oh, okay. So then let me see. It worked before. Okay.
Now it's coming. Okay.
Almost. See if I go stoppen. So let me see. Bildschirm freigeben. So now you should see it. Not yet.
No, it actually went away.
That's unfortunate because it worked before. Let me try, because we tried it, right?
Yeah.
It was fine. So let me now try something else.
Okay.
And now?
Yes.
It's in editor mode, not in presentation mode.
Okay, so now we need to start all over again. I stop it again. That's unfortunate. So, okay, one more time. Okay, but it should be this one. So now it should actually, no, it doesn't do it. Yeah, now it works. Okay, perfect. All right, so let me get started. So what I try to do today is, you know, I would like to connect the the understanding of the adsorption phase behavior fluids with characterization. And so in order to do an advanced characterization of nanoporous materials, it has been shown over the last 2 or 3 decades that fundamental understanding how adsorption and behavior and the effect of confinement on the phase behavior of fluids and pores, how this confinement effect changes the phase behavior of fluids and pores, and that can be a tool essentially to do an advanced texture characterization. So what I will do is I will give a little overview about adsorption characterization coupled with some of these insights in the phase behavior, and sometimes I will go quite fast because there are things I assume everybody has heard. And in some cases, I will focus a little bit more on certain aspects. So don't be surprised when I skip, when I show you some aspects and I skip over the slides quite quickly. But there's also, of course, for people who want to read more about it, there's literature given where you can read about it. So first of all, as you know, I'm since now exactly 4 years here in Nuremberg. In Erlangen, so Erlangen, Nuremberg, these are 2 cities. The one is more than 500,000 people. The other, Erlangen, is where the most of the campus is around 100,000 people. Everybody in Erlangen either works for the university or for Siemens. That's pretty much it. So we have one of the major Siemens research facilities here, and harbor also the technical part of the university, the technical faculty, which is more than 15,000 people. And so it's its own small, I would say, not reasonably big technical university within the University of Erlangen-Nuremberg, where we offer all types of degrees, from medicine to natural sciences, engineering, and so forth. So you can easily reach us now after Corona is a little bit better under control. You know, we can travel again, so you can reach us here from Frankfurt or from Munich. In both cases, you know, we have a only 2-hour direct connection with the train, or you can even fly directly to Nuremberg, which is actually 10 minutes away from the university. So when I talk about adsorption characterization, I always have to say this, that I'm a big believer in combining various techniques. It's not only adsorption you need essentially to assess the properties of a novel, you know, material. Usually it's the combination of different techniques like coupling adsorption with scattering, spectroscopy, and of course, most people also apply, you know, advanced methods of microscopy. But the interesting part is that these 3 methodologies, which I wrote up here in a, you know, little bit separated from these, physical adsorption, intrusion, and thermoporimetry, they all utilize the effect of confinement on the phase behavior to do essentially, you know, pore size analysis in particular. So if you have wetting fluid which wets the surface, then essentially, and we're thinking about the mesopore, then we're looking at the effect of confinement on the vapor liquid phase transition or wetting, you know, film. In case we use, for instance, mercury or another liquid metal, at the moment, for instance, we intrude here gallium alloys in porous systems, for instance, then you have a non-wetting fluid in the pores. But again, also here, the phase behavior is very similar or identical or analog to that what we see for wetting fluids. We see a confinement effect on the vapor liquid phase transition now of a non-wetting system. And of course, if we look at the effect of confinement on the freezing and melting points, then we can apply thermoporimetry. And when you see these different methods here, this is a scheme which we updated a little bit based on some work from the German Federal Institute of Reference Materials and NIST. You see that the combination of physical adsorption and intrusion, it covers a really wide range of pore sizes you can assess. You can essentially go from below 4 nanometer. Actually, when you use hydrogen as a probe or CO2 as a probe, you can go from 2.5, 2.7 angstroms up to almost like 400 micrometers and more to assess pore sizes. And if you utilize helium, which people also have done in the past as a probe, then you can even go to smaller pore sizes here. And you see, this covers the whole range of interesting pore sizes, while all the other methodologies, of course, have the sweet spots. And of course, it's very important to combine these methods, as I just stressed before. So let's stick with adsorption for this talk. And I decided to talk actually also a little bit about surface area, not directly correlated to the phase behavior of fluids and pores, but very important for the application of all of these porous materials. As you know, we use adsorbent materials for storage processes, for separation, because it's possible, due to the revolution, I would say, in material science, people can architect now nanoporous materials with properties really targeted towards the application. So the idea is to find the structure property relationships. And for this, in order to optimize, therefore, such applications, like gas storage and separation and so forth, and catalysis, of course, it's really needed to, essentially advance also these characterization methodologies. And surface area, of course, is one of the key ingredients. First thing you really need to know. Then, of course, you want to assess pore size and volume distribution, again, also in collaboration with advanced electronic microscopic methods, for instance, what we're also doing here in Erlangen. And there was huge progress over the last 20 years also to assess from adsorption data, but not only from one adsorption isotherm. You need a little bit more. You need like a couple of adsorption isotherms under certain thermodynamic conditions. You need some more advanced ways of doing the experiments, such as scanning of hysteresis loops and so forth. And this allows you then also to obtain information about pore geometry and structure of pore network. Important also surface properties, how they affect adsorption behavior, and how you can detect whether fluids are wetting or non-wetting. We will not have the time today to talk about this in too much detail. So let us start with where the understanding of phase behavior directly connects with characterization. So of course, you know, these kind of classification of physics-option isotherms. So I will not go into detail to discuss them. But what I want to do is right away in the talk is to see, you know, we have a new isotherm type here, the type 4b, which essentially shows a reversible condensation in mesopores, while typically people believe when you have a mesoporous system, you know, the capillary condensation occurs with a hysteresis. So this is the first, you know, this is a clear signature, as I will show now, of the effect of confinement on the phase diagram of a fluid in these pores and how this affects the shape of the adsorption isotherm. And in turn, of course, one has to take this knowledge into account if one wants to analyze this adsorption data with regard to obtaining information about pore size distribution, and so forth. So here's a scheme again, you know, everybody, so this is one of the slides I go very fast over. These are like snapshots of the different stages during the adsorption on a model, you know, slit pore here, or essentially cylindrical pore here, where you have adsorption on the pore walls, and then multi-layer adsorption, and then essentially have a region where this hysteresis occurs, where you have to overcome huge nucleation barriers to condense fluid in the core of these pores. And this is actually the jump here from the configuration C to D. But for the desorption, for finite pore in equilibrium with you know, with a reservoir, you do not need to nucleate any new phase. So therefore, the evaporation process is really happening at the thermodynamic equilibrium chemical potential, and therefore, you know, you just see how the molecules evaporate to receding meniscus. And this can now be a little bit elaborated further when you look at these different stages which are just introduced, by trying to understand why, you know, how to understand these hysteresis in this ideal system. And so we're picking two temperatures, T1 and T2, and T1 is farther away from the critical point, while T2 is closer to it. And you see what's happening when you go along T1, you see all the stages. But instead of seeing the condensation happening at the binodal, you have essentially to go very close to the spinal. In experiments, this happens close to the spinal, not exactly at the spinal due to fluctuation. And this is a typical situation of a homogeneous nucleation process, because you have already prior, you know, you have a liquid film on the pore walls, and essentially you have to nucleate a new phase in the middle of the pore. So this happens as like a spinodal condensation. But you do not have to do this when you essentially desorb, and then the evaporation happens right at the binodal. On the other hand, when you go to a temperature close to the critical point, right, then essentially you see that then the binodal and spinodal, of course, merge, and you know, in experiments, thermal fluctuations are sufficient, even when you're not exactly at the critical point, that you essentially do not see any kind of metastable range here, and then you have an isotherm which is completely reversible. And this also translates then in such a very schematic phase diagram. Please, I just want to really point out, this is really schematic. The slopes here, essentially, particularly at the triple point regions, are certainly, you know, certainly a little bit more rounded, but these plots serve their purpose. As I say, so you have here the situation again. Now, however, for two pore systems of different pore sizes, W1 has a critical point because there's a larger pore than W2, so the critical point is not as much pronounced. And now imagine a Rankine experiment where you start here at a given temperature, and then you do an adsorption experiment. You start at 0 pressure, and then you move up here, you know, with increasing the pressure. And then essentially, when you hit this pore condensation line, the vapor pressure line of the confined fluid, you see that for the small pore, you're essentially very close to the pore critical point, actually in a region which is above the so-called hysteresis critical point, where, as I mentioned before, in experiments, thermal fluctuations are sufficient to overcome nucleation barriers very close to the pore critical point. So you see essentially reversible capillary condensation. And then, of course, when you go, you know, at the same temperature, however, for the larger pore, you're much further away from the critical point, but also you're further away, of course, you know, below this hysteresis critical point, and hysteresis develops, and you have to overcome these nucleation barriers. This schematic diagram, of course, is strictly speaking only applicable to a very slit pore, where you really have true, you know, criticality, both in the bulk, but also in the pores. All right, so this shows very nicely how how confinement and the effect on the phase behavior and the phase diagram has direct effect on the shape of the adsorption isotherm here on the hysteresis. And it's clear that in order to extract information about pore size and pore size distribution and pore network information, you really need to take this into account when you analyze these data. And this cannot be done by macroscopic classical approaches such as the Kelvin equation. You need here advanced approaches based on statistical mechanics, such as advanced molecular simulation or mean field density function theory and so forth. Here's some recent examples which very nicely show the effect here of confinement on the phase behavior and on hysteresis behavior. This is a highly ordered mesoporous carbon, and you see that for CO2, we're first interested very much in CO2. You see a 0 degrees. We have still 30 degrees below the critical temperature of CO2. We see condensation without any hysteresis here, and we need to go to extremely low temperatures to see the development of hysteresis. And we see vapor liquid phase transitions here actually below the triple point, which is 216 Kelvin. And by further analyzing this data, so we're looking here at 5 nanometer mesopores, that we have here also a shift of the triple point. What's happening here is a vapor liquid phase transition below the bulk triple point. So we have an undercooled, CO2 liquid-like state in these pores. And when we would further, like we show here in the semi-log plots, when we then further essentially, increase the pressure, then we would see a sublimation in the bulk phase. So the bulk would be solid, but in the pores, we still have a supercooled liquid. We find here a really huge shift of hysteresis critical temperature, really anomalous behavior, and also a shift of the triple point. So this is and then this was confirmed when we go to another carbon, but now we looked into hierarchical pore structures. So this is a zeolite which has, mesopores in the order of 4.2 nanometer, leading to micropores. The idea is that this hierarchicality essentially, allows transport properties to become, much more efficient. And that's of course important for catalysis, for instance, where, reactant molecules will go much faster, easier into the micropores of the zeolite where catalytic reactions happen, but very importantly also the product goes out faster, which then avoids the poisoning of the zeolite. And we're investigating right now, the data are not published yet, but we're investigating how hierarchicality might also affect separation processes in our lab. Here we see it's something completely anomalous. We see that for these mesopores are slightly smaller than the one we had for the carbon, 4.2 nanometer, but we find here between the triple point of CO2 and the critical temperature, the bulk critical temperature, the bulk triple point and bulk critical temperature, only reversible capillary condensation of CO2. Okay, so I just chose here isotherms, even down to 240 Kelvin, we don't see any kind of history. Even at 210 Kelvin, which is, just below the bulk triple point, we don't see any hysteresis. So this is very unique. And on the other hand, also extremely interesting for applications, because if you consider, having, for process where you do separations and so forth, where you have not to consider this hysteresis behavior in such narrow mesopores, that's really, really useful. We see then the formation of hysteresis, far below the triple point at 195 Kelvin. And again, by analyzing these data, we come to the conclusion that we still have here supercooled liquid essentially in the pores, and here would be then the essentially sublimation, this sublimation in the bulk phase. So that is essentially, we've now extended this work to methane, and we are able to map the complete phase cycle of methane in this type of hierarchical zeolites. But I will, these data are just being put together for publication. So this should give you an idea how exciting this essentially is from a fundamental point of view, but also how important it is to take this type of confinement effect on the phase behavior into account for essentially, for characterizing. And I will come back to this a little later in my talk. So now very quick, for certain reasons, I want to give some small comments about the T surface area, because that's such an important topic, and it's discussed at the moment quite heavily, partially also in a way which is not, I would say, always straightforward. So, I can go now very fast. This is the famous BT equation, and strictly speaking, they should be working for isotherms of type 2 and maybe also type 4a, where we have no micropores in the system. And then Brunert and Teller said, wow, if you analyze the adsorption data in a range from 0.05 to 0.3 in relative pressures, which is here this axis, then you should be able to back out from this data the monomer capacity. And if you then know essentially how much area a molecule takes on the surface, the cross-section area, you can calculate then essentially the surface area. Now comes the first complication. For many years, of course, nitrogen adsorption was considered the main, the classical way of going, but nitrogen has a problem. So nitrogen is a rod-like molecule, and it has a quadrupole moment, which makes it quite complex when you have a surface with polar surface functionality. In this case, nitrogen, as I show here, might not necessarily lie on the surface. What it does really on carbons, where you have very often not many polar sides. But if you have polar sides, due to the interaction with the quadrupole moment, nitrogen can be tilted. And then the effective cross-sectional area is, of course, not that what people usually assume in all standards, in all the literature, that is around 16.2 angstrom square, which assumes that you have maximum contact with the nitrogen molecule on the surface. So leading to a real problem that when you assume the traditional cross-sectional area, which relates to that of a lying nitrogen molecule, that you might really overestimate the surface area if you have polar surface functionality. The problem is you really don't know what the surface chemistry is in most cases. So you don't know the effective cross-sectional area of nitrogen. Otherwise, you could essentially adjust for that, right? So that's a real problem. So you find, therefore, when you look at even simple silica surface and so forth, you find quite big differences, up to 20 to 25% between the nitrogen surface area, assuming the classical cross-sectional area, and the argon surface area. On the other hand, if you go to carbons, the surface areas between, I mean non-microporous carbons, of course, surface areas between nitrogen and argon is pretty much the same. Same, we tried also looking at fully hydrophobized silica surface, also the same. But if you go to a surface with polar surface functionality, we have this problem. So here you would overcome this problem by taking a probe molecule such as argon, which essentially always has the same orientation on the surface. In order to look into this more in detail recently and to prove this in a completely independent way, and now I go quick, I just refer you to the literature. It's also mentioned already the idea in the UPAC recommendations from 2015, but also very recently in collaboration with Gudrun Reichenauer from the Center in Würzburg, which is one of Germany's leading institutions for applied energy research. We looked into into analyzing model silica materials which do not have any type of microporosity. We did this with nitrogen and argon adsorption, and then we applied systematic small angle X-ray scattering experiments on these materials. And of course, when you do small angle X-ray, you have to, it's a completely different methodology, different technique, no assumption about cross-section areas and so forth is necessary. And here you see, when you look at just as the nitrogen argon data, these huge differences which you observed here, like for this type of silica and to this type of silica, this is quite a lot, 162 meters square per gram compared to 202 from nitrogen. That's quite a huge number. And these are non-porous, essentially silica, so you get a perfect type 2 isotone where the BT methodology really can reliably apply. When you now compare this with the SAX data, you find a perfect, without going too much detail, but paper is just published 2 months ago, you find perfect alignment with the SAX surface area and the argon surface area in this case. Another advantage, of course, when thinking about applications of SAX for quality control, for pharmaceutical industry, maybe, for instance, you can essentially, for these samples which don't have microporosity, you can essentially just take the sample, put it in a SAX machine, you don't need even to outgas it, and you can get extremely fast here the surface area data. So with this, essentially, one confirms essentially that indeed, it's of huge advantage to take the right probe molecule. On the other hand, a real problem is if you have microporosity, as you all know, and here and I really want to stress this because of so much literature which I recently, reviewing and so forth, where this is being really mixed up. The BET theory cannot describe, what's happening in a micropore. Essentially, what's happening in a micropore is that you have micropore filling, and you have completely filled the pores essentially already when you reach a relative pressure where you would expect based on the BET theory to see this formation of, or to have enough molecules adsorbed that you have a statistical model there. So here you have essentially completely full pore. And therefore, essentially you cannot apply, strictly speaking, the BET theory on materials which have on data obtained on materials with microporosity. And then, of course, what you can get is just the BT area, not a surface area a priori, which is an apparent surface area. And then in order to at least find ways to compare the data between different labs, Rucker-Roll et al. Have suggested, criteria which you apply in order to find an unambiguous way this linear range. Not going to detail to discuss this. This had been discussed many times before, and people still, develop new methodologies to even, more efficiently apply to Rucker-Roll methodology. But this gives you, at least when you apply this, you find a linear range. You see a huge difference in the BET area from 1167 compared to that what you obtain when you apply the BET theory here, the classical range, where you don't have linearity. But it's still, this has to be really being stressed. That's still not really a true probe accessible surface area. It's still a parent surface area, and either to prove that this is really a true surface area, you have to do, some additional work. So now something completely new, which we're doing right now here in Erlangen, is that we are actually, all the characterization methodologies, which we essentially have discussed so far, for BET and based on gas adsorption, they all are methods where you have to try or to, even prepare a sample in a vacuum situation. And, but many applications, such as, for instance, chromatography, works with a liquid mobile phase. And now imagine you have a surface which is functionalized, maybe with long chain alkanes. And now the mobile phase in chromatography, interacts with these, long chain alkanes, and this might essentially, block when they interact. These kind of chains might block accessibility to certain regions of the porous network. So the idea is essentially we should develop also methodologies which allows us to characterize, nanoporous materials when they're in applications in solvated form, surrounded by or inserted in a liquid. And there are not too many options we have. One of them, which we now look very carefully and very rigorous, is the application of NMR relaxometry. And what you do here is you put a sample in a very weak magnetic field, you switch this on for a certain time, very short time, and then, if you do proton NMR, the protons go out of their place, you switch it off, and then you see how the protons relax. You can do spin-spin or spin-lattice relaxation observations, and this is, for instance, for the spin-spin relaxation. And then you observe that, for instance, for the pure water, these relaxation times, this means when the magnetization is back to normal, protons are all back in the original state, takes much longer as if you have samples which have like a silica column. This is a stationary phase material for chromatography. This has a high surface area. You see this, the relaxation is much, much faster. So you can develop methodologies essentially which allow now to obtain from analysis of these data, surface areas. I have to say the methodology had been introduced already two decades ago into the petroleum industry, but in a very empirical way. What we really do here is trying to rigorously develop this and further develop this methodology in order to obtain reliable surface area and also pore size information from nanoporous materials immersed in the liquid phase. And here we get first really good successes. We have here the bar, we demonstrated that for such silica materials, the argon BT is much more reliable, and we find here quite good agreement with the with the data from analyzing such NMR relaxation spectra. And the same also for carbon flex, just to give you the insight what we're doing. Now, in order now to go to pore size analysis, one needs to understand now the effect of confinement on the underlying density profile of this liquid, and the wettability plays an important role on these pore walls or on surfaces. And in order to get a microscopic view on this, we started to collaborate here with Alex Namak, my PhD student Carola Schlumberger, who essentially, works this project, which is funded by the German Science Foundation. Just spent 3 months at Rutgers University to do the very first, I would say, the very first molecular dynamic-based simulations in order to look into the details of relaxation of a fluid confined in model pores. So just to give you an idea that this is something which is really important also, not to do only things in the gas phase, but also really look into application in liquid phase. This is one example for doing this. We do some other things as well, but I just want to highlight that. So now very quickly, before we go even deeper into this phase behavior story, which is already, as I mentioned, you have seen this already, how this is connected to characterization, very quick to pore size analysis. And here, the narrative is argon, of course, stays. If we have a problem with nitrogen, that it interacts due to quadrupole moments with polar surface functionality, that's of course, as it has been shown, that this has a huge effect also on the effect of pore filling, which pressure or chemical potential pore filling happens in such materials such as zeolites or metal organic frameworks, which all have polar surface functionality. And also here, argon at 87 Kelvin is therefore the suggested adsorptive to do this. This is a suggested probe atom to go for this. Now, if you, however, have really highly tortuous, disordered ultramicroporous carbon, then even argon might be too big to get into the very, very tiny pore, or there might be diffusion restrictions. Even if it would fit into the pore network in some of these active carbons is so tortuous that it will take a long time for argon to essentially adsorb in these pores. And then CO2 adsorption, 0 degrees, is a key tool for doing this. And if you have low surface area materials, and also krypton adsorption is the standard methodology. So let's stay first with this very quickly, just so people have not seen this. So here comes another very important point which I want to make. And you saw, and I had a slide before which essentially demonstrated this, the importance of looking at your data. This is for the experimentalists, that you, particularly, when you look at data, which essentially have micro and mesopores in the system, particularly with micropores, it's extremely interesting to plot these data in a semi-log plot. This allows you to see the quality of your data, but particularly see, the structure of your porous system. Look at this wonderful, hierarchical structures. You see, of course, in linear plot, you just see this is the filling of micropores, but not much difference between this kind of samples. And you see, of course, what happens in the mesopore range. But when you look at semi-log plot, you see here the filling of, in this case, a Y zeolite. This is a hierarchical zeolite, as I mentioned. There's a Y zeolite of 1.2 nanometer cage connected essentially with the mesoporosity. And this also is demonstrated in this kind of classical picture, which I wanted to show for people who have not seen this. These are series of industrial zeolites, endomorph, okay? And now so fast. And you see when you plot them linearly, you see just differences in the plateau values, type 1 isotherms, just showing different pore volumes. But if you plot it semi-logarithmic, you see right away for this argon data that the pore structure must be different. See, the mordanite has here channels of 6.5 angstroms and side pockets. And you see here, filling of the side pockets below 5 angstroms, that is between 6 and 7 so roughly 6.4 angstroms are these channels. And then you see here the cesium 5 zeolite, which is, of course, is a 3D network of elliptical-like pores of 5.2 angstroms. And the pore filling happens here right between, here the pores below 5, here's between 6 and 7, here's 5. So you see just from this plot, based on the crystallographic data which we have for such zeolites, that you can obtain here pore size information on a 0.1 nanometer level with argon, which is not that sensitive to the surface chemistry and adsorption as with nitrogen or other fluids are. Of course, then you can analyze this with advanced methodologies based on density functional theory. And, see here, we can really resolve these narrow process distributions. Here's the bimodal processing from the mordanite. And right in the middle between these two peaks, we have the cesium 5. And this, of course, is how what is called this, I would call it state of the art right now. So state of the art in pore size analysis is essentially to apply methods based on statistical mechanics, based on DFT, pioneered by some people in the audience, like Keith Gavins in 1993, suggested, non-local density functional theory in his work with Hysteresis applied on carbons. And then Alex Nymark opened up a complete new array of methodologies to characterize micro and mesopores with different pore geometries and pore sizes. And these are essentially, the methodology which we apply, which should be applied. And it allows, contrary to the classical methods, which are listed here, to obtain with one single method, you can assess the whole pore size range from micro to mesopores. And here's an example. First of all, of course, I have to mention that the classical methods, because they cannot, and this is now the connection to the one of the initial slides, when we have reversible capillary condensation, the disappearance of hysteresis cannot be described by methods based on the Kelvin equation. So when you're looking at now narrow mesopores, say below 20 nanometers, but particularly when they're below 10 nanometers, all these classical methods cannot describe accurately the adsorption isotherm and its correlation to pore size and geometry. So you get huge underestimations of pore size. This is the BGH method applied on this wonderful data obtained on an SPA15 silica, highly ordered mesoporous molecular sieve, and that is what you get from density functions. Where this agrees with what you get from independent methods, which you can use to obtain the pore size of these kind of highly ordered mesoporous molecular sieves. And you can also obtain, in this case, you can analyze both the adsorption and desorption parameters for the pore size analysis, because this advanced DFT approach will allow one to take quantitatively into account for given pore size and geometry, the delay in condensation due to these nucleation barriers, which we discussed before in my talk. So you have a beautiful tool set which you can then apply, that you can obtain reliable pore size information from adsorption when you look for more complex system, like this one. This is again an example of a hierarchical zeolite. You see here the linear plot, and you see here again the semi-log plot, and you see that we can obtain with DFT the whole pore size distribution, micro mesopore range, and the corresponding plot of the pore volume. So you don't need anymore to apply a T method to obtain a micropore volume. You can read it right away from this cumulative pore volume plot. This is the micropore volume, and from here you have the mesopore volume. So that is actually the only way essentially to analyze such hierarchical pore structures. Here are some examples where these have been applied, and same for ultra microporous carbons. Here's a classical example where CO2 adsorption was combined with nitrogen argon adsorption. You get the combined micromesopore analysis here of such an hierarchical carbon material, which is used as a supercapacitor. And I'm very happy to say that I've started to collaborate again with Rod Ruoff, who moved from Texas essentially to South Korea. And at the moment we're working on a very common paper where we're looking into templated carbons templated with zeolites. As you all know, and most of you know, is that the advantage of CO2 at 0 degrees compared to argon and nitrogen. I indicated this already. This was suggested by Rodriguez-Ranoz and co-workers and Professor Linares long time ago. The limitation is, however, that you only can make this apparatus which only goes to 1 atmosphere. You can only access pores below 1 nanometer, because the saturation pressure of CO2 at 0 degrees is almost like above 30 bars. And if you only measure to 1 atmosphere, you have a relative pressure of 10 to the minus 2 only, and this only allows one to access pores below up to 1 nanometer, I would say. And this is why you have to combine pore size distributions from different fluids, here CO2 and nitrogen in this case. No? So now we recently, Alex Naimark's group and my group, we looked at the question, could we not then essentially maybe measure the full isotherm of CO2 with a high pressure apparatus, and then analyze these data in order to obtain the full pore size distribution just from CO2. And we would serve here 2 reasons. First of all, people who are interested in assessing a nanoporous material for CO2 storage capacity and applications, they have to measure the high pressure isotherm anyway. So why not then taking this data, and you have the full adsorption capacity, and obtain by analyzing it the pore size distribution just from CO2. And I'm not going too much detail. We did this with did experiments on model materials, again on CMK3, found some very interesting phenomena about this, that hysteresis would not appear over a large range, as I just mentioned before. Of course, the complexity is also to measure surface excess. You have to convert these to adsorbed amounts to do some thermodynamics. But at the end, by applying advanced Monte Carlo simulation methods developed by Silvidantes and Alex in cooperation with us, we could essentially then we can obtain pore size analysis from CO2 data, micro and mesopores, roughly up to 9-10 nanometers. Now, of course, this carbon story doesn't end when essentially one has to look at the effect of heterogeneity. This is also an old story. I just mentioned it here for completion, and there's still work going on. I know that Fred also works, and also the effect of pore geometry on adsorption, which has to be taken into account. So I want to cut that short. There are ways in order to introduce heterogeneity in this kind of advanced DFT models, such as in quenched solid density functional theory, but also other methodologies are available. So I'll skip this. just to say. And here is very important. This is something where also Fred works on right now. This is something that people usually forget. Very often when you do pore size analysis, people are not sensitive towards the assumption of a certain pore geometry, but the absorption potential is of course a function of both the, the size of the pore and the geometry. And in this cartoon here, you see here for slit pore, a cylindrical pore, and a spherical pore, they all have the same width, okay, or pore size if you want. But the absorption potential is in the spherical pore much higher than in the slit pore, which leads to the point that in the spherical pore would fill at much smaller relative pressures than the slit pore would fill. Here you need more pressure to fill it because the absorption potential is less. And if you now apply not a proper pore geometry model on the adsorption data, you can make catastrophic errors. For instance, here is a hierarchical mesoporous system, which has spherical mesopores and has some connected micropores, but we're looking at the mesoporosity. So these are spherical pores. And so here you see the difference between if you apply the spherical pores, that is the true pore size you would expect here. But if you apply a cylindrical model, you underestimate here the pore size more than 35%. So it's 35%. So this is quite a lot. Just to keep this into account. So when you apply these advanced methods, you need to also take into account what pore geometry might apply. Now, if you go from geometry and from pore size now to something which is, having pores connected in a pore net, which is essentially, usually the case for adsorbents, then this is the last part of my talk. I will give some, ideas about how you can essentially understand the pore network based on an understanding of the adsorption phase pair of fluids and pores, in particular, in a sense, how these effects contribute to the shape of hysteresis loop. So I want to know how much time do I have left, so I don't want to overtake my time too much. Fred, how much do I have?
You can use, what time is it? You have more 10 minutes.
10 minutes, wonderful. So we're good in time. Then I just want to make sure that that will be fine. So then everything is good. So we can dive now into that kind of story. So first of all, I will only now focus on some interesting aspects here, and for people who have not worked in this area too much and want to understand here the basics much more, I recommend here, a recent tutorial like review, which we were invited to write. This is a PhD student of mine, Carola Schlumberger, and then also a couple of years ago, we published in a quite comprehensive review on how one should characterize hierarchical structured nanoporous materials. So there you find quite a lot of information how advanced adsorption methodologies can be applied. Of course, we always hint how important it is to combine these techniques with complementary techniques to obtain information about how the pore structure looks like. So here, the first hint you find also in these UPAC recommendations from 2015. Essentially, you look when you have a hysteresis, you spin off a complete new classification of hysteresis loop, which is also in this paper. And we're going now to explain a little bit more very quickly what we can learn just from the shape of the hysteresis loops already in a very oversimplified way with regard to pore structure. So this ideal case we already have discussed, where we have essentially no type of pore blocking or pore network effects. And in this case, we will see, the hysteresis as an only consequence of this delayed condensation, which is coming from these nucleation barriers. However, the situation becomes more complicated if, in addition to this delayed condensation, we have, pores which have necks. Okay, so in this case, like a series of pores, ink bottle pores, which have a similar, different pore body sizes, but they have a certain given neck size. So in this case, they have different cavity sizes, but the neck size is the same. And then also in this case here, this is a more classical picture of a porous system where you have like a narrow neck and all the liquid, which essentially adsorbs here as a function of pore size. So the adsorption branch is correlated with the size distribution, but the desorption is essentially very steep because the liquid which is trapped in the pores C and B can only leave if you reach a pressure which is associated with the size of the neck. Okay, so this means that this explains this asymmetric hysteresis loop. So we fill pores here according to their size, but during evaporation, you empty the system when you reach a pressure associated with emptying the neck, but then all liquid gets out at once. And that is a classical percolation transition. And so in this case, we can obtain, as I mentioned, the pore size distribution information from adsorption. And for doing this quantitatively correct, we need now to apply such a model, for instance, the mean field density function theory model, which takes into account in a quantitative way, this kind of delay of condensation as well. From the desorption, when we analyze these, we will only get information about the characteristic entrance into the pore system. So everything empties when we empty the neck. This is quite different when we go to this case where so-called cavitation happens. So in this case, the necks are essentially much, much smaller, okay? And they're below a certain critical size. So when they're below a critical size means that, we reach essentially the pressure of the liquid vapor sperinodal of the condensed fluid in such a pore. This pressure is larger than the pressure needed to empty the neck, okay? So in this case, you can have a situation where you empty essentially the cavity, but the neck still remains completely filled. And then you empty the neck essentially at a much smaller pressure, which is now then again correlated quantitatively with the size of the neck. Okay, so in this case, if this happens, then essentially you have no correlation of the desorption branch with the neck size, which was essentially here the percolation transition the case, and also is of the case when you have an H2B hysteresis where you don't have a pore connectivity like this, but now a pore connectivity more like the, as you can see in certain ordered silicas like KT5 silica, for instance, but also in certain carbons and other materials, mesocellular foams, for instance, where you see that you can, you empty each essentially ink bottle, according to the neck size. So the desorption branch corresponds to the neck size distribution, while in this case you have a very narrow distribution of pore cavities, and therefore this is so steep. So just by this simple interpretation of some of this characteristic hysteresis loop, you see we have here a correlation between the underlying adsorption mechanism and phase behavior in pores and essentially the pore geometries and also pore connectivity. And here again, this is from this kind of tutorial. Here you can explain essentially with this kind of schematics, you can explain the difference between pore blocking and cavitation. Also, again, based on the phase diagram level, we're looking at binodals and spinodals. So where is this important? So first, this is important for many things, but here is something which is one of the caveats, the pitfalls you find in characterization. And you have to repeat this every 4 or 5 years. You have to show it to students because every 5 years is new generation students, and very often papers show the same mistakes. So this step down here in these isotherms is essentially cavitation-induced evaporation. Okay, and so this means that when you have here, this is a hierarchical zeolite again. You see the filling of micropores, then you fill some mesopores, but here you have very large pores, mesomacropores. And some of these pores have narrow entrances, and they empty. So the pores, these large pores, they empty here during this kind of step down is due to cavitation. So this means that the peak you find here when you analyze the desorption branch, this is not, this pore size here is absolutely an artifact. So actually this peak should happen at much, much larger pore sizes, but it's just artificially here at this place because of the cavitation due to evaporation from these large pores due to this kind of narrow necks. And I would say like this critical width, which I have mentioned, is roughly 5 to 6 nanometer if you look at nitrogen and argon adsorption at the body temperature. So everything above 5 to 6 nanometer will give pore blocking, everything below, if the neck is smaller, give this cavitation transition. So this is something you then also know. If you have cavitation happening, you know that pores are connected in an unfavorable way. You know that you have not large pores leading to small pores as you really would like to have for advanced transport phenomena, but the other way around. Here is a more drastic example. This is a really classical alumina catalyst support. So very wide distribution here you get from the adsorption branch. And then you see this very extremely perfect peak coming from analyzing the desorption branch. And I've seen cases where people thought they have an extremely narrow process distribution. Of course, the opposite is true, it's extremely wide. So beware of this kind of pitfalls, which are due to cavitation. In the past, in old textbooks, this step down was discussed within the concept of the tensor strength hypothesis, which is related, but doesn't describe the tensor strength hypothesis, doesn't describe the nature of the cavitation-induced evaporation, because cavitation can only happen if you have a connection between a larger pore and a smaller pore in type of ink bottle geometry. So very quick, there is a, meanwhile, one has developed in the field a comprehensive toolkit for physisorption toolkit for pore network analysis. And you can find a lot of this in these two, review papers, which I mentioned. So therefore, I want to just, in the interest of time, just go to the tool which are called scanning of hysteresis loop, because this can be done. This is a really powerful tool, but also still you have more questions than answers here. More experiments are needed on model system to completely understand these kind of scanning layer. This is why I want to mention it. Want to also motivate listeners maybe to dive into this type of research. So I go right into this, and here is the idea. So you have you would have an adsorption isotherm with the H1 type of hysteresis. So we already learned that this happens when you have quite regular pores where you do not have any type of pore blocking. So usually this is the case in many cases, not always, but in many cases. And then you see here, if you would fill the particle, say, assume an angstrom 41 particle with many cylindrical pores which are independent from each other. If you fill this particle only to a certain extent, say 2/3, 60%, then you measure the adsorption hysteresis, you see that this called desorption scan hysteresis loop looks the same like the boundary curve. Okay, in this case, the mechanism of evaporation and condensation has not been changed, whether you fill the particle completely or only to a certain extent. This changes, of course, if you have a system which gives rise to this percolation transition, because usually you would have this percolation, pore blocking driven evaporation when you have a situation where none of the fluid here has really access to the outer world, only through this narrow next. But if you fill now these particles only to a certain extent, then you might have next pathways open to the interior of the particle, and now liquid can evaporate without blocking, and therefore you see that this desorption scan curve is completely different than the boundary curve in this case. So this indicates that when we only fill the particle to a certain extent, we remove the pore blocking effect here. And by analyzing such data in a systematic way, this was pioneered by Douglas Everett, de Boer, and many others, you can get information about pore network connectivity and other things. But as I said, more work is needed on model systems because in order to get more light into this, in this interpretation of scanning curves. Here's, I think, what we safely know. So if you have a system where we have independent and open pores, the boundary curves and the scanning curves look in shape very similar. So this kind of hysteresis looks the same as the boundary curve. If you have percolation transitions, we find that then these kind of scanning curves, they have a different shape and they end in the lower closure point. That is typical for percolation transition, the pore blocking happens. If you have cavitation, then of course the environment of a cavity doesn't play any role, because the evaporation of the liquid from the cavity is entirely controlled by the thermodynamics of the confined fluid in the cavity. Essentially, it will go out through bubble formation, through cavitation, when you reach the liquid vapor spinodal, and it doesn't care where they have what the connectivity says. So in this case, essentially the scanning curves look again very similar to the boundary curves and very similar to the situation where you have a system of quasi-independent pores. Of course, you have here pore network, but the mechanism determines here the scanning curves. Okay. So here's some examples. This is what I want to say. We need more, work where we do very careful experiments, and then of course coupled with molecular simulation approaches to understand how in very fine, well-defined materials the scanning curves really look like. So here's an example. It's a highly ordered KT6 silica, and here is a very fantastic material. This is a hierarchical silica which has micro mesopores of around 5 nanometers and large. very large cavities of on the order of 30 nanometers. And you see here, we know that this is cavitation. And you see the scanning curves go right into this kind of desorption branch, as I, have showed in the schematics. So this is the deal. This is what we want to do. Essentially, convert finally, this information into pore network information and quantitative distribution of maximum cavities. So, but the last two slides will now essentially summarize a lot of these kind of things which I have mentioned in this talk. And we will combine now, as an example on the hierarchical structure, the understanding of how phase behavior actually utilize the effect of confinement and phase behavior to visualize the pore network of the system, and therefore to improve essentially the accuracy and the reliability, therefore, of course, of the pore size distribution. So this is a series of hierarchical isotherms on the hierarchical zeolite, where the mesopores were introduced with essentially, using surfactants as structure directing agents. Okay, and you see here, when you go to larger lengths of surfactants, it's a typical MC41 synthesis. Then essentially see here how the mesoporosity, becomes larger while the microporosity stays the same. So we take one of these samples out, and then we essentially coupled this kind of approach with world-class, electronic microscopy and tomography. And with this, we could show that indeed, essentially these mesopores and the micropores are really connected in a hierarchical way, meso to micropores, but it's not possible to quantify this sufficiently just based on this kind of electronic microscopy approach. So now we couple this with advanced gas adsorption, high resolution argon adsorption, with hysteresis scanning and so forth. And this allowed us to determine the intercrystalline mesopore volumes and differentiate between truly accessible mesopores and those are constricted. And this summarizes my talk now very much. So here's what we see. We have nitrogen and argon adsorption here on such hierarchical zeolite. The mesopores is 4.2 nanometer and the micropores are 1.2 nanometer. So now when you look at this hysteresis group, they look very regular. They look like essentially like this is type H1 hysteresis. So everybody was happy when they saw this and say, yeah, all the mesopores leading to the micropores, but not so fast. Because look, when you look at this pore size distribution, we know from understanding of the phase behavior, which we discussed before in such a phase diagram, that when you have narrow mesopores, like roughly 3.6 nanometer below 4, they give rise to reversible capillary condensation, while larger ones have essentially hysteresis. So this means that we essentially have here a certain amount of pores which do not contribute to hysteresis. So we do know nothing by looking at hysteresis based on the pore connectivity. So now in order to visualize the contributions of these pores to the overall hysteresis loop, we now apply the following trick. We know that when we now lower the temperature, so we somewhere here, for these 3.6 nanometer pores, we lower between the hysteresis critical temperature and the pore critical temperature, we lower now the temperature sufficiently that we can make all the fluid in these narrow mesopores subcritical with regard to the pore critical point and hysteresis critical point. And by doing this, you observe a completely change in the shape of the adsorption isotherm. You see two-step isotherm. And now in order to find out what this step means, we did the scanning curves and we see, yeah, these scanning curves, they go right into the step, which indicates this must be cavitation. So the conclusion was there are these step down comes from mesopores, which essentially are not leading to the micropores, but embedded in the micropore framework. And so with further analysis of these data, we're able now to quantify the percentage of open mesoporosity and so-called restricted mesoporosity. And you can apply this methodology, which we published some years ago already, to many other systems, and allows you essentially then to correlate this structural data with transport properties. Okay, and this allows people now to tune essentially during the synthesis process the properties of the materials in this way that you can fine-tune them for the application with regard to transport and so forth. So with this, I come to the end. Sorry that I took a few minutes more, but I hope I was able to show that it's possible and needed to to understand how confinement affects adsorption phase. Hysteresis behavior. We talk not so much about wetting today in order to obtain reliable information about the pore network. It's actually fun. It's fundamentally of interest, but as I said, this is a very nice application to this. So first adsorption, yes, is a powerful tool for characterization. And when you then understand details much more even and combine this adsorption with other complementary technique, you can then really obtain quantitative details about pore network and what pores are really contributing to transport potentially and what others are not. This is my last slide. I think, of course, my team here, Alex Naimark, who contributed over the years in characterization a lot, also Katie, when I was scientific director at Quantachrome, she was I developed her to be my right hand in the field, and so she contributed to particularly the first part of the talk about the hierarchical structure characterization, which we did at the end. To this paper, she contributed a lot, and then of course would like to acknowledge also funding agencies. Thank you very much for your attention.
Thank you so much, Professor Thommes, for this amazing presentation. We are now open for questions. So if you want to ask one, please feel free to enable your microphone or write it down in the chat so we can read it. All right, so who wants to be the first one? Professor Miguel Jorge, please go ahead.
Hello, Miguel.
Thank you. Hi, Matthias. Wonderful talk as usual. I had it's a very small question indeed, related to the surface area measurements that you did on those reference silica materials.
Yeah, I go back.
Which have no microporosity, right? So earlier in your talk, I wonder if you've compared the surface areas, the BET surface areas, to geometric surface areas from software like Pore or something like that. Is that possible to do? Do you have a model of the structure that you can use to get this geometric surface area? Because I would say that if there is no microporosity, then in theory the BET area should be the surface area, as you said.
Exactly.
With microporous materials, not so sure, but yeah.
Yeah, absolutely. Yeah, we didn't do that yet, but it's a very good suggestion, Miguel, to do that. So we said, okay, yes, when we take materials and this has been proven before over the years, when you look at the very accurate calorimetric measurements done, for instance, in the Rucaro lab 20 years ago, 30 years ago, you could demonstrate that indeed, when you have a material which doesn't have micropores and not narrow mesopores, which in the order of 2 to 4 nanometer, that then the BET theory essentially can quantitatively be applied, and then you could consider this kind of area as a true, probe accessible area. But has not been done for such model materials to compare this with, trying to predict based on these advanced statistical mechanical models the geometrical area. But therefore it was, but what has been done, Miguel, is the following, So when these materials are usually, this is one of the reasons why we use SACS for it as well, small angle scattering, because it's completely independent method. And what has been done is the following. When you can make these nanoparticles so nicely nowadays that they're completely, the shape is very well defined. So you can calculate based on the particle size, which you can measure with advanced laser, diffraction or dynamic light scattering methods. You can obtain the geometrical area, okay, from these, and then compare with that what BET gave us. And the very first paper who actually highlighted that nitrogen might be problematic for such silica and oxidic surfaces was a paper from 1994, coming, I think, from a guy called Jelinek, I believe. And essentially, he applied dynamic light scattering to obtain particle size distribution on very well-defined, particles, and then compared this with nitrogen BET, and then came to the conclusion the nitrogen BET cannot be right. Okay, and then he postulated essentially that there must be a problem with the orientation, knowing the orientation of the molecule on the surface. And that was essentially when he then looked very back into the literature, when you go in the beginning of the 70s, and you look at very basic old papers by Kensing, also Rodriguez Reynoso, and also from Rucaro, then you find essentially clear hints that they already had the idea there must be something, not very well known about the orientation, but not having model materials, they couldn't quantify it.
Yeah.
Okay.
Yeah.
But this is a good suggestion. Thank you, Miguel.
Yeah. No, thank you. Thank you very much.
Can I ask a comment on question?
Sure, Professor.
Professor, thank you for your wonderful talk about Pore size and shape. My doubts are, in terms of modeling transport, how much pore connectivity is important? For example, would you recommend a side percolation or a bond percolation models in terms of?
Yeah, that's a very good question. We have a PhD student who is actually trying to tackle this right now in order to further advance this kind of network models. No? And I have to say, I have not yet, based on what we have yet now revisited all the older work also, and we have not come to a final good conclusion on this yet. What would be the better way on this?
Thank you.
We're working on this as well. Okay.
So basic question is, for example, you can model it as a connected processes or connected structure, like it's a bond percolation or side percolation. Which would you think, in terms of these micropores, you would advise?
Yeah, so I'm seeing this. So I'm trying to answer this question because I just mentioned that we're working in particular on building networks models, which are based on these two concepts right now to compare with the experimental data. But I would like to go actually a step on safer grounds right now, because what we see is what is really needed is essentially to couple, for instance, as in the last slide, so where we're able to. So let me go back this quickly, because I think it's worthwhile to makes this point clearer. So so when you have a certain, when we know the pore structure in principle, so this is a hierarchical structure, okay? And now by applying this kind of advanced methodologies, we can, for such a structure, mesopores and micropores connected. This is the overarching simplified version of this. We can pretty much from the data we obtain tell what is the percentage of pores which are leading to the micropores, and what is percentage of the mesopore volume which is not contributing to this kind of transport. And with this information, I believe what is needed is to take such materials where this structural information is available and actually do diffusion experiments. Careful diffusion experiments, and that could also, and we do not have this too much. I think there were a couple of papers from the Carger group, but also from there was a paper from the group in Montpellier, the Renzo and Anne Galano and others who tried also to look at hierarchical structure with regard to transport, but essentially to correlate such structural information with real transport properties. And having this experimental database might help us also to find a more proper avenue with regard to the modeling. Because in my opinion, we do not have enough good experimental data, both on the transport side and the characterization side on such model systems.
Oh, thank you, Professor.
Who wants to be the next? Do we have any more questions in the audience?
I have a curiosity. All my questions you answer already, so I have no exact question. But if I heard correctly, you are doing some molecular simulation for calculate NMR relaxation, is it?
Yeah, we do this essentially. We started doing this in Erlangen, but then of course we collaborate here with Alex Naimark, okay, from who's also in the audience, and my student Carola actually spent 3 months at Rutgers in order to start the collaboration between these two groups, because nobody has done that yet. That's the funny part. We were so surprised. This methodology, NMR relaxometry, I know from my adventures in the petroleum industry when I was in America, because at the time when they started with fracking, for instance, they suddenly were interested in adsorption and understanding adsorption isotherms, because for the first time they didn't have conventional reservoirs where the methodologies worked, at micropores. And I got invited very quickly to give talks at these like in Aramco and so forth. And yeah, then I discovered at one of these labs this technique, and I found out they started with working with this technique in the end of the 80s, with the idea that for people like Brian Kay and others who are working particle size, and they were thinking that with this technique they could essentially speed up the pore size and surface area characterization process. Problem was they never were able to really rigorously assess it, the technique. Okay, so therefore the petroleum industry applies this in a very empirical way, because it's the only technique, one of the few techniques, which only gives a signal when there is something in a rock, like a liquid in the rock, oil or whatever, right? So then we were surprised. So then we took it and started to do this kind of very rigorous work here in Erlangen. And when we presented this first results at a German characterization meeting, people who had applied NMR for years came to us and said, wow, why did we not do this? Because it is really interesting. And then, of course, the question comes, how does, so these kind of NMR relaxation spectra are, of course, correlated, in our opinion, with the intrinsic density profile of the fluid in the pores, of the liquid in the pore and the pore walls. And so in order to shed here some light, you need to do some systematic, simulations, in my opinion, to compare with experiments. And therefore, we talked to Alex. Alex was visiting me, and then we realized nobody has done that. So we started a collaboration. We got some funding to send a student over there, and so we see what we can do.
Very interesting. Let me ask you, what the role for the structural relaxation? Because sometimes you do a molecular simulation for relax the fluid inside the pore, but what the structural relaxation role in this information?
Yeah, if Alex is still here in the audience, and because Carola is just back, then Alex could maybe say something to it if he's still in there. Because we have not discussed yet we just started this, Fred. We have not too much information yet. We have, just worked 3 months on this. So I would not like to give any conclusive results here or statements.
Okay,
so,
very nice. The idea is very nice. I like that.
But the experiments already were difficult. It's a process of 2 years now to get the experiments right. This is the reason why we also looked at SAX measurements for surface area, because we needed true benchmark data. So we needed really to revisit surface area, take materials where we know absolutely the reference, what is the benchmark, real benchmark data, and then trying to develop this technique. And we have so much fun with it that now, I have to say, the first instrument I built when I came to Erlangen, I started to build an adsorption lab. Then people came to me and asked me, Matthias, we have no methods to look in the liquid phase characterization. And I said, how can we do this? And I thought about NMR, and that was the first instrument I installed. Now we have, 2 or 3. We'll get another one really, and we go really deep into this right now. And I think it's worthwhile. It might at the end turn out that it's not necessarily a widespread tool for getting the surface areas. It's only, we find out that the surface areas in these systems with the liquid are only different compared to that what you get from gas adsorption when you have really long functional groups on the surface maybe. But this is a very important result also, because then you can use this methodology to test wettability in a quantitative level, because the method only, is very depending whether you have a wetting film on the surface or not. So if you know the surface area from other means, and you know that for your system which you immerse in the liquid, this is the true geometrical area, you can obtain information about wettability. And there is, I see, to be honest, the widest application for this technique.
Yeah, I can add on this technical question. Actually, I was very surprised that we could not find any papers which could be referred to on modeling NMR relaxation in pores, because the problem seems to be very simple, right? So, for example, you have a water, and then you orient all the dipoles in one direction, you remove the field, and then basically it's like a Brownian motion. Yeah. But technically, it is necessary to calculate this dipole per correlation function, and then to take a Fourier transform to determine actually the curves which experimentally measured. Yeah, and this actually is there are some technical problems how to do this. Yeah. So Carola did a fantastic work, but this time was too short, basically, to complete this project. But again, I thought that we could find certain recipes in the literature, and we could not find. So if somebody could advise, would be absolutely great.
Thanks, Alex, for the insight.
I wonder the external field length scale for this for small pore, sometimes the external field is really the gradient for the external field is huge. So I don't know. I'm going to think about these interesting questions.
Yeah.
I have your comments on your T2 measurements. In the petroleum industry, I'm more familiar with. The T2 response of NMR was used to correlate all properties of petroleum fluids. For example, refractive optical property, refractive index, surface tension, as well as compositional properties. For some years it went on because it's cheaper way of doing it, people thought. Now it seems to have subsided a little bit. You think the T2 correlates more with transport properties or surface properties or thermodynamic properties or all of them?
Yeah, no, this is actually exactly the problem which I also saw when I worked with all these people in the petroleum industry. Very empirically, you know, they try to obtain from T2 also for T1, spin lattice, similar information, but there was not a clear correlation, a clear structure property relationship of the data they had. So it's empirical models. And so here, what we're doing right now in order to shed light into this, we take well-defined samples where essentially we know everything about their structure and we know everything about the surface chemistry. Okay, and now trying to understand how this T2 measurement would essentially correlate with one property, in this case, just the surface area. Okay, so we're not looking at these samples which we're using here are not porous. Okay, so again, just looking at one aspect. And if you understand, after understanding this, we go a step further and then take the same kind of surfaces, same kind of materials, like we're looking at carbons, carbon flex works pretty well, and the silicas, and then introducing, you know, confinement and porosity to it, and then see how this changes. Of course, we have to, and so with this, we try to entangle all these different contributions to the T2 or the T1, and then try to shed some light into this story and also have a clear methodology developed for utilizing this technique in a rigorous way for characterization. This is how I would like to tell you.
Okay, thank you. Thank you.
So do we have any more questions?
I think it's time.
All right, so I think it's time to wrap it up. So once again, thank you so much, Professor Thommes, for the presentation and for being here. And thanks everyone for the discussion.
Okay, thank you guys for inviting me. It was a real pleasure. I really had fun. So thank you for everybody who I saw on the screen. It's always a big pleasure to see friends and colleagues. And I really hope we can meet again very soon, also in person. You know, again, I'm happy that the traveling started again. And I hope that COVID-19 doesn't challenge us too much in the near future, also with regard to being able to personally meet each other. Have a wonderful evening. Best regards here from Alan. Ciao.
Wait.
Just for the final announcement now.
Who's going to?
All right. It's coming. All right, so for the final announcements, we just want to remind everyone that our seminars are being recorded and posted on YouTube after the lecturer's agreement. So if you want to check them out, please visit our YouTube channel. This is our seminar committee. We're responsible for communication with lecturers and hosting the seminar and doing all sorts of other stuff, such as certificate writing, and responsible for making this event happen. So these are the people that make it work. And next week, we'll be at September 1st, we'll be receiving Professor Doros Theodorou, who is going to talk about atomistic and mesoscopic simulation for the prediction of polymer properties. I'm sure it's going to be a great presentation, and I hope to see you all next week.
Wait. Doris is here. You can.
Oh, Doris. I'm sorry, Professor.
Doris
Please,
here.
if you want to give us a brief review, please go ahead.
Well, thank you. First of all, let me congratulate Professor Thommes for this very interesting talk that he gave. Well, in this talk that I will give in a week, I plan to talk about the challenges that we face when we try to simulate polymers, where we have extremely broad length scales, distributions of length scales and time scales, and how one could address those with simulation. So we will try to see how can one equilibrate, for example, a very long chain entangled polymer, how one can study its dynamics, how one can develop mesoscopic approaches based on atomistic simulations to address the very long time scales that one encounters in polymer processing operations, how one can deal with the very long times associated with the relaxation of polymer glasses, where with time properties change during physical aging, and also a few things about how polymers behave at interfaces. It will be a talk primarily directed at methodology, but I hope you can get something out of it.
Perfect.
All right, I'm sure it's going to be
Thank you.
amazing, and I hope to see you all next week for his presentation.